Good morning, everybody, and thank you for attending this webinar. I am Eirini Papagiakoumou, researcher at the Wafer Engineering Microscopy Group at the Vision Institute in Paris, and together with Ruth Sims, postdoc in the lab, we prepared this seminar. Today, we are going to present you an overview of the latest methods used for controlling and imaging neuronal activity. This means that we will not insist on basic notions about neurons' activation and functional imaging, since time is limited. So we hope that you're familiar with that at some extent. The use of light in modern neuroscience as a tool to monitor and more recently also as a tool to stimulate neuronal activity has revolutionized the field by changing the way neurophysiology experiments are done. Having acquired important knowledge on how neurons work individually, mainly by studies using electrical stimulation and recordings on single cells, neuroscientists now wish to understand neurons' function within their environmental circuit and eventually how a circuit interacts with other circuits, and all this with the appropriate temporal resolution, which should be of the order of few milliseconds in most of the cases. Due to the minimally invasive nature of photons, a plethora of optical technologies spanning these spatiotemporal scales have been developed, and as a result, optical activation and inhibition of specific classes of neurons can now be achieved using a variety of light-gated actuators, the opsins, and neural activity can be detected using highly specific and sensitive fluorescent probes, including calcium and voltage indicators. All this gave rise to the field of optogenetics about 15 years ago, which today has matured to such an extent that all optical experiments can be performed where signals from multiple neurons distributed even across different brain regions can be listed and recorded optically with single cell and millisecond precision. The most common approaches for optical manipulation and recording of neuronal activity rely on nonlinear two-photon excitation, which provides spatial localization of the excitation volume thanks to inherent optical sectioning and robustness to scattering due to the infrared wavelength used in that case. The gold standard for imaging in turbid biological tissue is, of course, two-photon excitation laser scanning microscopy by raster scanning of a tightly focused pulsed laser beam using galvanometric mirrors as a 2D scanner imaged at the objective pupil. And this has also been applied to manipulate neuronal activity. However, precise control of neuronal activity by opsins and high-fidelity readout of activity from calcium or voltage indicators often requires higher temporal resolution than what can be achieved by raster scanning based on galvanometric mirrors. Despite the fact that successful single-cell optogenetic activation using scanning to photon excitation based on galvanometric mirrors with spiral, random, or raster scan patterns has been demonstrated, the success of this approach is reliant on the relatively long decay constants of the order of tens of milliseconds exhibited by some opsins. Provided that the scan period is shorter than the opsin photocycle time constant, sufficient photocurrent can be integrated to appreciably change membrane potential and induce the cell to spike. However, pure sequential scanning to photon excitation approaches are not scalable to multi-target photoactivation because of the limited temporal resolution and the relatively long time needed to scan from one cell to the other. A large number of different techniques have been developed to overcome this limit, which can broadly be classified as either scanning or parallel methods. In the first category, different approaches are applied to enable faster scanning of the laser spot, while in the second category, regions of interest are illuminated with spatiotemporally shaped patterns of light. Let's start from those methods that use scanning to photon excitation to maximize the rate at which a tightly focused beam samples several predefined regions of interest. The total scan time in that case is defined by the time to remain on a site to induce a physiological effect, the so-called dwell time, plus the time needed to move from one site to the other, and all this multiplied by the total number of sites. The dwell time depends on the properties of the photosensitive sensor used for imaging or activation and the physiological properties of neurons, so there is not much improvement that can be achieved there by optical means. To decrease the time to move from one side to the other and achieve kHz rates, especially for imaging, researchers have used other types of scanners such as regional galvanometric mirrors, rotating polygon mirrors, and acousto-optic deflectors. The latter was also used successfully for rapid displacements of the beam in the axial direction, although the optical system gets quite complex in that case. Other components capable of rapidly varying the axial position of a tightly focused beam include deformable mirrors, spatial light modulators, piezoelectric scanners, MEM systems, MEM scanners, electrically tunable lenses, voice coils, or tunable acoustic gradient lenses. Interestingly, alternative approaches specifically designed to improve volumetric imaging rates rely on the conversion of lateral beam deflections, typically using galvanometric mirrors, into axial displacements at kHz rates. This is, for example, the case in this work where authors scan a laser beam laterally in a remote focusing system, and the beam is then back reflected from different heights of a stationary mirror in image space. If on the return path of the back reflected light, the lateral scan component is perfectly compensated, a pure axial scan motion at the rate of the employed lateral scanning technology is obtained. The authors used two variants of this concept, one capable of performing discrete axial steps using a staircase-shaped mirror, and one capable of continuous axial scanning using a tilted planar mirror. You see here the result in both cases. The acquisition rates of scanning two-photon excitation systems can be further increased by random access scanning, a technique which commonly uses 2 or 4 acousto-optic deflectors to rapidly deflect a tightly focused beam to a set of predefined three-dimensional locations. Random access scanning has been successfully applied to both calcium and voltage imaging at kHz sampling rates. Here in the examples that we show, first, for calcium imaging, the authors have used 4 acousto-optic deflectors in a compact design with high-speed electronics to perform 3D random access pointing scanning and continuous line scanning over the entire imaging volume. They also implemented the random access patch scanning for defining imaging patches intersecting the regions of interest. In the more recent example of voltage imaging of the sensor ASAP3, the authors used 2 acousto-optic deflectors in what they called ultra-fast local volume excitation strategy. This is based on applying non-stationary frequencies to acousto-optic deflectors to rapidly scan a holographically generated array of excitation foci in 3 dimensions. In this way, they selectively excited large membrane areas at rates of up to 15 kHz per cell. Scanning methods have also used spatiotemporal multiplexing to increase the acquisition speed. In fact, the fundamental upper limit to acquisition rates in fluorescence microscopy is the fluorescence lifetime, which is of the order of 10 nanoseconds. Since the fluorescence lifetime is shorter than the repetition periods of pulsed lasers used for two-photon excitation, single pulses can be divided into multiple excitation beams, which can be laterally or axially displaced to illuminate the different sample regions at different, almost simultaneous times. By accurate synchronization of the excitation beamlets with a detector using high-speed electronics, sequentially excited fluorescent signals can be demultiplexed. Contrary to line scanning, parallel approaches increase the temporal resolution of two-photon excitation by modulating the electromagnetic field to increase the instantaneous volume of excitation. One class of parallel approaches use phase modulation of liquid crystal-based spatial light modulators placed at the plane conjugate to the objective back focal plane. By performing computer-generated holography, we can spatially multiplex the excitation beam to project the multiple diffraction-limited spots in 3 dimensions. light modulated by the SLM is deflected to different three-dimensional sample position according to the applied phase mask, which is calculated in that case by a superposition of grating and lens effects. Spatial multiplexing by computer-generated holography has been applied for both photostimulation and imaging. A common approach for photostimulating neurons uses spatial multiplexing in combination with a pair of galvanometric mirrors to laterally sweep each focus in a spiral motion spanning the average diameter of a neuron. The number of beamlets and their position can be dynamically updated up to the SLM refresh rate, which so far in standard models was 60 Hz, but this tends to change as faster SLMs are coming to stage. Notably, a recent study showed the development of a very fast liquid crystal special light modulator that could reach 500 Hz of refresh rate, and presented a system with two SLMs operating in what they called the burst mode operation, where both SLM1 and SLM2 are preloaded with the necessary holograms, and each is sequentially illuminated to expose the sample to an optogenetic illumination pattern with a sequential temporal difference limited only by the gating time of the focal cell. When such systems are combined with high peak energy amplified femtosecond laser sources, hundreds of excitation spots can be simultaneously generated. Specially multiplexed calcium imaging using a spatial light modulator has been combined with both single pixel and camera detection to show enhanced signal-to-noise ratio. In the latter, a Gaussian Laguerre faceplate in the detection path extends the imaging depth of field, enabling 3D simultaneous detection on a 2D camera without axial scanning. Here we should mention that other methods for extending the depth of field of the detection point spread function also exist in the literature, but we don't have the time to mention them here. Very briefly, we would like, however, to mention that full-frame calcium imaging at 1 kHz acquisition rates using parallel spatial multiplexing by generating a grid of beamlets using a microlens array has been also recently demonstrated. In the previous examples, parallel approaches are combined with scanning to increase the excitation volume. Full parallel two-photon excitation approaches use phase modulation to increase the lateral extent of the excitation beam in a scanless way. Full parallel approaches are time limited only by the dual time of the physiological process under study, and such methods include the use of computer-generated holography for projecting arbitrary excitation patterns or generalized phase contrast and interferometric-based technique that transforms a phase modulation to an intensity pattern. For applications that use parallel illumination to activate or image neurons only on their cell soma, large low numerical aperture Gaussian beams have been also used. Lateral beam shaping is generally combined with temporal focusing to preserve axial resolution, which scales linearly with lateral extent for holographic beams and quadratically for loosely focused Gaussian beams. In temporal focusing, we take advantage of the dependence of the two-photon excitation signal on the pulse duration, and we create an axial temporal gradient in photon density that enables optical confinement. In other words, the pulse duration is modified along the axial position, and fluorescence is excited only where the pulse is short enough, which is the temporal focus. The optimum axial resolution that can be achieved in that case, as you see here, is equivalent to the one of two-photon line scanning excitation microscopy, but in a completely scanless way. This is because the intersection of the grating plane used for creating the temporal gradient of photons with a laser beam at each moment in time is a line. Actually, temporal focusing performs line scanning at the speed of light, briefly. Techniques for distributing temporally focused light throughout the three-dimensional volume have been developed as well. In that case, a special light modulator is placed at the Fourier plane of a temporally focused beam that can be a large Gaussian or a generalized phase contrast or a holographic beam, as it is the case in this example. And the second SLM performs spatial 3D multiplexing through computer-generated holography. Convolution of the two patterns of the excitation pattern plus the diffraction limited spots of 3D computer-generated holography gives rise to the projection of replicas of the initial spot to the predefined positions encoded on the multiplexing SLM. Temporally focused low numerical aperture Gaussian beams have been used to rapidly scan in big volumes for fast monitoring of neuronal activity with calcium imaging, as it is as we show in this example. Generalized phase contrast and holographic patterns have been used with temporal focusing or not for neuronal photostimulation, especially for optogenetics, since parallel to photon excitation methods can simultaneously excite opsins distributed throughout the soma. Photocurrents can be efficiently integrated with parallel methods independently of the photocycle, which facilitates control of neuronal activity with millisecond time latency and sub-millisecond spike jitter. Concerning the combination of methods for two-photon excitation and imaging of neuronal activity, despite the diversity of instrumentation available, most two-photon all-optical experiments performed to date have used galvanometric scanners, both resonant or not, together with electrically tunable lenses, as you see here, for performing volume imaging of the calcium activity. This is mainly the result of the physiological properties of calcium indicators, which can generally be adequately sampled at 10 Hz. Further to the techniques we have already presented, another category uses transverse elongation of the excitation beam by using light sheets and reducing scan to one dimension, similarly as in line scanning to photon microscopy. Transverse scanning of axial elongated beams, such as Bessel beams, has been also applied for volumetric imaging. In most cases, elongated foci result in the projection of axial information onto a two-dimensional recording, but this can be overcome using spatial demultiplexing methods again. So before closing, we should mention that the techniques presented here are just a sample of what exists in literature, where one can find many variants, especially for two-photon scanning microscopy. And still, we haven't mentioned anything about three-photon microscopy, the emerging imaging strategy for reaching deep layers at depths over 700 of micrometers in scattering brain tissue. And we haven't mentioned anything about techniques enabling imaging in a mesoscopic level of different brain areas being millimeters apart. So with this, I would like to thank you for watching, Ruth for the help to prepare this presentation and for helping answering your questions right after. And finally, Sophia Lach and the RTMFM for the invitation to give this web seminar. Thank you for listening.